So Prashant Kamat is here as a speaker online. You can see him on the screen. Prashant, nice to see you. Prashant has been head of the field, or has been a leader in the field of optoelectronic materials for many decades. He's really a very established star in our research field. He's worked on many different things, from quantum dots to graphene to heterostructures. And in the last years, he's focused more and more on hybrid metal halide perovskites. Yeah, there's so much to say. I mean, there's so many prizes he's won. He's published, I think, on Google Scholar, almost 1,000 entries in his Google Scholar. And but I think what I find impressive about this is that he's had this very successful career. He's among the top 100 chemists, I think, without publishing many or maybe even any Nature or Science papers, right? He's published a lot of stuff, a lot of really highly cited and very good work, but he's mostly avoided the very shiny journals. So maybe that's a lesson for all of us to focus more on the content than on the journal impact factor. Speaking of impact factor, he's also the editor-in-chief of one of the most impactful journals in the field, the ACS Energy Letters, that in very few years he's built up to one of the really most well-read journals in the field. So that's also one of his tasks. But today, he'll of course talk about the perovskites, and he will talk about directing energy and electron transfer in cesium-lead bromide nanocrystals. So Prashant, the floor is yours.
Okay. Thank you, Bruno, for a very kind and introduction. So probably it's all the students who do all the work, and I get to deliver it. So I should thank all of them first. Coming back to your impact factor, so when you can't publish in a high impact journal, create one. So that is the message. Anyway, so I'm going to talk today on some of this work that you have been engaging in energy and electron transfer processes. So the other side of this metal halide perovskites has, again, majority of the work is focused on solar cells, but they also have other properties. You can make these very fine quantum dots. And one of the questions that comes is how to do it. So just to give you back, there may be some younger audience. How does all the renewable energy started? Actually, it started in 1970s when there was a OPEC oil embargo. And at the time, the artificial photosynthesis was coined to mimic photosynthesis. And that led to a lot of studies involving photo-induced electron transfer processes. It also gave birth to the semiconductor photoelectrochemistry. So if you want to learn some basics of semiconductor photoelectrochemistry, there are excellent papers by some of these people who have listed in the here. And these were sort of my inspiration. They are great visionaries. So you can go and look into the paper. Majority of the work we are doing today, what they proposed at that time, whether it is a photocatalysis or light energy conversion or those kind of a thing. So then moving on, 1980s and 90s, popular topic was environmental remediation using photocatalysis. TiO2 was a perovskite at that time. So everybody was gung-ho about learning more about how to manipulate photocatalysis. Solar fuels was also started and continued, and today it's another hot topic. Dye-sensitized solar cell was also emerged. And probably this is one of the first major breakthrough in terms of trying to use this mesoscopic electron transfer layer, that is TiO2, and then various combination. From there, we went down to quantum dot solar cells, OPVs. So that led to this quick emergence of perovskite solar cells. As Bruno mentioned, we have been using a variety of heterostructures, and I'm not going to talk about it. But just to give an idea how these nanostructure assemblies gives you an idea to functionalize them, to putting together two particles on an electrode surface or in solution and modify their properties and behavior. So just to give an example of those things. But in this kind of a heterostructure, when you create, the two major processes dominate. One is energy transfer, another one is electron transfer. Just to give an idea, in the earlier we have done it, where combined TiO2 and cadmium selenide with a bifunctional squarene die. In case of carboxylic acid, functionalized squarene group attaches to TiO2 and a thiol group attaches to cadmium selenide. And we can individually establish FRET energy transfer to the die, and this one injecting electron to the TiO2. So that was one of our early effort in understanding. And again, these kind of processes are involved in nature's photosynthesis, in imaging processes, a variety of different processes. And now the question is how good we can understand through these perovskite nanocrystals. And when it comes to energy transfer, you can get singlet energy transfer or a triplet energy transfer between a donor and an acceptor. So donor and acceptor. So same way in electron transfer, you transfer only one of them, electrons or holes, and we call them reduction or oxidation. But now the question is, how does this semiconductor nanocrystal decides whether to transfer energy or an electron or hole? So again, that is sort of a question, and what are the factors that determine which way this energy can be transferred to the bound molecule? So that is the one thing we are doing it. So again, the motivation comes from semiconductor nanoparticles is traditional photocatalyst. You can create various different oxides, chalcogenides, and these ternary oxides. So people have been looking into this. But when it comes to lead halide perovskite, you can change the composition either through A-side cation or halide composition. You can tune the entire bandage. And again, this is copied from one of the review articles. So this gives you a nice one. So another one is also, there is a very similarity between a molecular system and a semiconductor system. In molecular system, we talk about singlet ground state, singlet excited state, which you put energy in to create, and that can radiatively recombine, or you can generate this triplet excited state where the relaxation is much slower. Same way you can semiconductor quantum dots, we call it as a band gap excitation, and then they can recombine back the charge carriers radiatively or non-radiatively, or it can also get trapped and create a very long-lived excited state. So there is some similarity exists between the two while considering this one. So again, these materials have high intrinsic PL quantum yields, composition tunable light absorption, participation in both energy and electron transfer. And again, they have been trying to use them in photocatalysis, LED applications, a variety of other ones. Okay, so now coming back to energy transfer versus electron transfer. So we are going a little deeper now. So you have this semiconductor nanocrystal, and it's very easy to say, okay, we are transferring energy. So what we are transferring? Are you transferring singlet energy or a triplet energy? Is it a Dexter mechanism or a Foster mechanism? So all these questions suddenly arise. So that's what I'm trying to give you some glimpse of it and how we can do. And here is one of the studies like Upconversion. They add like a ruberine and a DBP, which is a perylene dye, and then excite with 800 nanometers and generate a 600 nanometer, 10 nanometer light. So what is the mechanism that underlies in this one? They do claim that you transfer electron and holes to create this excited state, which is essentially a Dexter mechanism. And then it undergoes triplet to give you this, two triplets will give you an excited singlet, and then they will transfer energy to this DBP to give you this upconversion. But the underlying mechanism is not been, although there are papers, I will show you one paper where it is wrong, but one needs to get more clear picture. Same way when it comes to electron transfer, there are several aspects controlled. The more important thing is how nicely the molecule binds and what are the energetics that dictate to transfer electrons or holes selectively. typically in photocatalysis, what one does is they take away one of the charge carriers, like for example, using a sacrificial donor in a large concentration. And that leaves the other charge carrier, for example, electron, a long life to reduce the molecule. Furthermore, the bound ligands can create some problem because that can influence the interaction. Here is just one example where these perovskite nanocrystals were used to generate hydrogen from hydroiodic acid, HI. This is not a water decomposition. So basically they claimed that any decomposition through holes was compensated by this iodide and the electrons were used in hydrogen. Okay, this is the outline today. I'll give you two examples, one with the energy transfer to rhodamine B dye. Another one is electron transfer to methyl viologen that we are going to use it as a probe. Okay, let's take a simple experiment. And this one, anybody can see it. It make a cesium lead bromide nanocrystals and just add rhodamine dye. And then you can see the emission mainly dominates from the rhodamine dye. So there is a paper came in 2020. It says triplet energy transfer. Okay, in the triplet energy transfer means this is sort of the energy level. So it is bypassing the singlet. So it is straight away going to the triplet. So although this is a favored process for singlet energy transfer, the paper claimed that they're transferring into triplet. They did for cesium lead chloride and also cadmium sulfide. So this sort of got us curious to see whether singlet is doing it. So we did the very simple experiment one can do. Just go on adding rhodamine B, and we excite at a wavelength where rhodamine B does not absorb. And clearly you can see as you increase the rhodamine concentration in micromolar concentration, you see a quenching of this cesium lead bromide emission. At the same time, you are seeing an increase in the emission of rhodamine B. And you can see here that's an enhanced image of this region. So that leads to the other one is we got about 88% of energy transfer by comparing the donor and donor acceptor system. Okay, so this tells you that it is deactivating the cesium lead bromide. But again, the question comes, can you do the reverse way, where you keep the rhodamine B concentration constant, but now go on increasing the concentration of cesium lead bromide? As more and more light absorbed by cesium lead bromide, you would expect more energy transfer. And sure enough, so this is the rhodamine B without any cesium lead bromide. And the moment you go on adding cesium lead bromide, you are seeing an increase in the rhodamine B emission. And we can take this one and plot it. And here at this wavelength around 600 nanometers, 587 nanometers, where the peak is. And if you just do cesium lead bromide, very small emission at this wavelength. But the rhodamine dye will starts increasing as you increase the cesium lead bromide, again confirming the interaction between the two and transferring singlet excited state energy. Another clue, this is the rhodamine B fluorescence, the spectrum A, which gives you around 575 nanometers. And if there's a phosphorescence, it is further down. It's a lower energy. So you should see only around 650, 660 nanometer region, and we don't see that. So we have no evidence for triplet energy transfer in this system. So it comes exclusively from the singlet excited state. Another clue. So this is another thing I strongly advocate. If anybody is looking for any kind of a new emission band or establishing an energy transfer process, record an excitation spectra that tells you where the emission is coming from. This is the spectrum when you get cesium lead bromide and rhodamine, showing you the peak at cesium lead bromide and rhodamine. So we are monitoring it at further at 650 nanometers, way down. So in the previous one here, so we are monitoring right down at this wavelength so that we can cover entire range that is there. So, and this is the spectrum of the cesium lead bromide and rhodamine B. And this is what you get from the individual spectrum. If you have only the cesium lead bromide, you get the spectrum here and the rhodamine B here. So essentially what you are getting, the gray spectrum, is the composite of the two. And so even when cesium lead bromide, you are seeing emission at 650. So it further confirms that it origination from cesium lead bromide. So we did the transient absorption spectroscopy to see the time scale with which this energy transfer occurs. So again, people who are familiar with this technique, where we do the sample and bring a pump laser and probe with the white light. And we delay the white light to see how the spectrum changes. So this is a difference absorption spectrum where the excitonic band bleaches as you generate charge carriers and they recover back. So we can also do the same thing with rhodamine B. And here is the slice, the time scale. You can take a slice and then see what happens, that kinetics. If you look in the rhodamine peak, which is down here, which you see here, a very small bleach that comes in. And if you have only rhodamine, you see a bleach, and this is a long-lived. So within 500 picosecond, very little decay because it is a longer lifetime of a few nanoseconds. And on the same scale, if you add rhodamine B and cesium lead bromide, you see there is a small rise in this one. And again, this matches also with the bleaching recovery. So here it is, the rhodamine B increase in a very short time scale, how it increases. So that gives a time scale with which it transfers energy. So here is the rhodamine B bleach showing you an increased bleach. And here is the fast recovery of the cesium lead bromide, giving you the same kinetics. So this confirms that we are indeed getting the singlet energy transfer. So again, the question comes is, how can we do it, prove it? Because what is the mechanism behind it? And what we did was, we varied the band gap of this donor, in this case, semiconductor nanocrystal. So we can make cesium lead bromide and exchange with chloride ions at different levels, and you can see, and you can tune the band gap. And the reason we did was to vary the overlap between the rhodamine B absorption and cesium perovskite halide nanocrystal. So that's what it is. So this is what your rhodamine B absorption spectra looks like. That's this one. And these are the emission spectra of different perovskite nanocrystals having different chloride bromide ratio. So as you can see here, this is cesium lead bromide, and the shaded area is the overlap between the two. And that overlap integral comes both in the Foster and Dexter mechanism, but they have a different relationship. So again, they are distance dependent, and other one is a overlap. So since distance is constant in this one, we can just focus on this overlap and see how this overlap influences the rate constant for electron transfer. And here is the rate constant for electron transfer that we estimated, and this is the J overlap integral between these emission of the donor and absorption of rhodamine dye. What we see here is if it was a completely Foster energy transfer, we would have followed these blue traces. So it would have dropped down as we move away from the overlap. Whereas what we see, the measured one, is we still get this different higher rate constant for energy transfer. That's a measured one. That shows that when there is an overlap, it is most likely the Foster energy transfer. And when there is less overlap, it is dominated by the Dexter energy transfer, where you transfer both electron and holes. So again, that's the one. So why we are seeing the singlet energy transfer? Again, because it is a favored energy transfer, because you don't have to undergo spin inversion and those things and those one. So typically we see triplet only when the singlet energy level is higher than this conduction band energy. And those are examples like anthracene, pyrene, and those things where the singlet energy is higher. In that case, we can see the triplet energy transfer. For example, this one is done by Phil Castellan's group. They tethered functionalized pyrene and naphthalene and anthracene. I think this is the example of anthracene where they connected it and then they observed the triplet energy transfer again to the transient absorption and various other techniques. And they were able to see the triplet energy transfer in this case. What is new now is coming up is 2D perovskites, where one can use these kind of ammonium functionalized pyrene, anthracene, and naphthalene, and they can be used as a spacer cation. And we are also seeing these kind of a thing. So this is currently we are looking into this kind of a systems. So stay tuned for the next one. So just to summarize, what I said was through quantitative control of donor acceptor spectral concentrations and overlap, we find the evidence for singlet energy transfer. As I showed you how to do it carefully, follow up the singlet energy transfer processes. We did not find any triplet energy transfer to get in the case of rhodium B. Even we tried generating triplet and to see it. So transient absorption spectroscopy revealed the time scale. It can occur within the 200 picosecond. And both Foster and Dexter type energy transfer mechanisms is operative. Okay, so now after sharing that, in the next part, I will focus on the electron transfer process. And just to go through, this has now a major thrust in many different research programs is to make solar fuels, either to make hydrogen or reduce CO2 into some kind of a value-added chemicals. This one is, again, remarkable why this is gaining. So this has come out in this March from Denmark to accelerate development of green fuels. They are putting 1.25 billion. Japan, Australia, UAE, everybody is considering now putting renewable energy, either wind, solar, coupled with a electrolysis to generate hydrogen, and then you can store it and then deliver it. And hydrogen is also not only a good fuel, but also a good reducing agent. If industries can use this hydrogen as a reducing agent, it can save a lot of carbon footprint in this one. So just to give you an idea, but to probe this directly, the hydrogen production on a semiconductor surface is pretty difficult. So what we do is we use probe molecules like a methyl viologen, which is the first step in electron transfer process to generate methyl viologen radical. So again, there is a recently summarizes all the perovskite photocatalysis in this perspective. Okay, so one of the things we wanted to see is, does the surface chemistry matter? So we had different ligands. This is the oleamine oleic acid ligands. And here we use a lead sulfate oleate shell. So this really is an inorganic shell, an excellent synthesis for somehow it is not being picked up by the community, but it's a very good synthesis where you can even prevent mixing of the two halides. And another one was DDAB ligand. We can exchange it. So that is a little more stable doing. So we looked into it. So we see this adding methyl viologen, the first fingerprint is the quenching of the emission. And this quenched emission can be used to calculate the equilibrium constant between methyl viologen and cesium lead bromide. It assumes that all the quenching you are seeing is because of the formation of this associated complex. And by using this double reciprocal plot, you can calculate the apparent association constant for this equilibrium process. So essentially what it's telling you is when you are using 10 raised to 6 micromolars, most of it is adsorbed state to the bound state. So again, you can do with these three different ones, and you can calculate these association constants. They're quite high. So then we did the transient absorption spectroscopy to see the formation of how fast they are decaying. So with the different the cesium lead bromide. And so this is with no methyl viologen. This is how they decay. But when you put methyl viologen, so what you're seeing is a residual bleach. You see here, for example, is most of it is recovered in 1500 picosecond. There is a quick bleach, but there is a residual bleach. I will come back to you in a minute why we see a residual bleach. And here it is. So this is in the, if you look into the first 50 picosecond time scale, you see this slow decay. But when you add methyl viologen, there is a fast bleach recovery followed by a sustained bleach. We can use this fast bleach to calculate the electron transfer rate constant using this difference in the lifetime. And so we get these different values. So they are all fast. They are of the order of 10 to the 11. So that tells you that the bound electron transfer between this nanocrystal and methyl viologen is an extremely fast process because it's in a bound state. So there is a summary of how the different surface interactions matter. So it looks like all of them are strongly bound. There is a small variation between the association constant, but they are quite high. As a result, we get a very high charge separation. This is the initial charge separation that we see. We have also independently measured through the methyl viologen radical formation. And you can see here the values are very close by in that things. So now I mentioned about this bleach, the sustained bleach. And one of the reasons why you see that is because this methyl viologen that is bound, it feels that it is part of the nanocrystal. It's like another ligand. So when the electron is transferred, the electron gets stabilized in the methyl viologen, but the holes remain in cesium lead bromide. So there is a direct communication between the two, like creating a dipole. As a result, it still sees as a charge separated pair. So that's why we extend it. But again, it is not lived forever. So if you do the longer time scale, it decays with a 30 nanosecond time scale. So what we have done is now created this electron hole pair that lives longer. It's an extended charge separation through this relay. So now if you want to transfer this one to another electron acceptor, one can do that by just giving a longer time window. So that is the one thing that we do. So I'm just coming close now. So wood capping of perovskite nanocrystal. So I have to also warn you that these were done with a triple solvent because the cesium lead bromides are very sensitive to the polar solvent. So we have to use like a few percent of toluene, esternitrile mixtures to get this one. But then we came out is, can you provide an inorganic shell? So again, what we did was cesium lead bromide. It's a two-step process. So we made them and then treated with this cadmium DT, this ethyl compound of cadmium. And we heat it for an hour and we can get this a very thin capping on the top of cesium lead bromide. And again, you can characterize the absorption emission spectrum. In fact, the emission yield goes up because the surface remediation of the traps. And we can confirm the presence of cadmium and sulfide to the elemental analysis. Okay, so we did the same experiment down here, transient absorption, and followed the recovery. Now you can see the difference between with and without shell. So without shell, we see this sustained bleach because of this extended charge pair. But when you put a CDS shell now, it's sort of, you break that barrier. So now the viologen is attached to the CDS. So we no longer see this one. Instead, we see a faster recovery with the viologen system. So, but that is also what it does is, as it transfers, it suppresses the back electron transfer also. So as a result, we can do now steady state photolysis with significant, we can add even 15, 20% ethanol. It's very stable. And and just you shine the light in a thing, and you can generate a steady state evolution of this radical, and it is shown here, absorbance at 608 nanometers. So this is done with the light that is more than 400 nanometers in light, and then you can generate this electron transfer product. And we get about actinometrically about 8.4%. I also have to tell you that the ethanol that is present here drives away the holes, and that's what it makes the stability. Another thing we can do is how do they equilibrate this one? So using this redox couple, it is an old method of using a Nernst equation to find the flat band potential of semiconductor nanocrystals. Typically, we always assume that the band positions are same as in the bulk. But in a colloidal suspension, given all the surfaces with the different molecules, different environment, these bands are not same as the one you or expect to have from a solid state point of view. So what you do is you vary the concentration of your ethyl viologen and get the steady state concentration. At the steady state, there is a forward and back electron transfer match, and they maintain it. And that is dictated by this flat band potential. So you just plug in your whatever ethyl viologen that you produced here, radical, and the difference between the two is your oxidized form. And using this Nernst equation, you can carry this flat band potential. So, so this is another way you can also use it to make it. To summarize this one, I gave you two examples. Cesium lead bromide nanocrystals can participate in photoinduced energy transfer as well as electron transfer processes. Depending upon how it is bound to the surface, their energy levels, it dictates this one. For energy transfer, either you need to have Foster trap energy transfer, or you have to transfer both electrons and holes together to generate the singlet excited state. That's a Dexter mechanism. On the other hand, in photocatalysis, you can transfer only one. In especially like methyl viologen, the energy level is very high, so it cannot transfer energy. The only pathway is it can readily transfer electrons. And how do you facilitate is take away the holes by, in this case, ethanol. So that gives you longer time, so you can generate in steady state electron transfer. So I hope I gave you sort of an insight into how these molecules interact with these semiconductor nanocrystals and participate either in energy transfer or in electron transfer processes. So these are some of the people who do in work. And again, I wish I would have been there to join you in discussing more, but hopefully I will get another chance to see you. Thank you again.
Thanks, Prashant. We also all hope that you will get a chance to visit here at some point in the near future. Thanks for a very nice talk. We have time for a few questions. Who would like to start? Yes, please wait for the microphone. And Prashant can also hear you. Esther.
Yeah, thank you for a wonderful talk. I was triggered by one of the images in your first slides, around maybe 10 or 12. You showed the luminescence of this molecular system as a function of indeed, this on the top right graph. And I was surprised by the fact, maybe it is expected, that the increase in luminescence is non-linear with the concentration of these crystals.
Yeah, because what happens is there is an absorption thing involved, right? So the absorption does, once you pass the Beer-Lambert's law, the absorption is not linear. Most of the absorption is near the closed surface to the cell, and it doesn't not uniform. That's why, in fact, you will start seeing a decrease at the high concentration. This is not coming from the system. So what the linear region is only at low concentrations when absorption of the cesium lead bromide you add is linear. So this non-linearity in this one. So this one was just done to in the previous here when we did was not this one, sorry. Yeah, in this example, we kept the cesium lead bromide concentration constant and added the rhodamine B, because the domination at 400 nanometer is typically cesium lead bromide. So here we do not have that absorption problem because at the excitation wavelength, this one doesn't absorb. But when you have this system here, the cesium lead bromide emission just goes up. So if it is absorbance is say 1, then the non-linearity in the absorption within the cell kicks in.
Okay, thank you. Other questions? Yes.
Hi, thank you very much for the nice talk. I actually have a following question on the same slides. I'm just wondering, what are the solvents that you use to dissolve the cesium lead bromide nanocrystal and the solvent to dissolve rhodamine B? Because I think the cesium lead bromide cannot be very stable in a polar solvent, but on the other hand, with carboxylic acid at end group, you might have difficulty dissolve rhodamine B in a less polar solvent. So how does the system?
Yeah, right. That is true. Sometimes we use a small amount, maybe 1 to 2% polar solvent to dissolve rhodamine B. If you see it, the concentration of rhodamine B is in micromolar concentrations. They are not very high concentrations. The previous study which I showed, they just took the crystals and just sonicated it, and then they assumed that it is absorbing. But in our case, we did dissolve. And the paper here gives you all the details. Where is it? Somewhere. Yeah, here. So this is Jack's paper. We are given all the experimental details. And there is another compound you can also try with the thiocyanate that binds much stronger than this one. Even 1 or 2 micromolar is fine to see this energy transfer.
Okay, we have time for one very short final question. Patricia.
Hi, this is Patricia Schulze from Fraunhofer ISE. Thank you for your talk. Cadmium sulfide, can it also be a good electron transport layer for tandem solar cells or for perovskite solar cells?
Yeah, in fact, if you look at the First Solar, their commercial product, it is cadmium telluride and cadmium sulfide they use. There they use, I think, cadmium sulfide as one of these electron transport layers.
So maybe there's a chance also for perovskite cells in the long
run.
Yeah,
you know, like one of the things, again, I was in Garden conference this week in perovskite solar cell. Most of the community tandem solar cell is trying to improve silicon solar cell, rightly so, because silicon has one of the highest efficiency. But there is also an opportunity to modify this cadmium telluride, cadmium sulfide, because it's a commercial product too. So if we can improve the cadmium sulfide, cadmium telluride solar cells, that is another opportunity for improving that efficiency. So maybe First Solar can be more interested in those ones too.
All right. Thank you for that. In the view of time, we have to stop here, but let's thank Prashant one more time for a virtual visit.
Thank you. Thank you very much.
Okay, thank you, Prashant, and see you sometime soon in person. Bye-bye.
Yeah.